Okay. Hi, everyone. So today we are going to talk about queuing, queuing theory. I'm just curious, does anybody got a chance to work on this special topic, queuing system, queuing theories before? Okay. So you know the queues are nothing but waiting line, right? It's a waiting line. So obviously queues are part of our everyday life, is that right? And we all wait in queues to make bank deposit or buy some movie tickets. I've been to the movie theater over the weekend, but fortunately I didn't wait that long. Anyway, so also people waiting to obtain food in the cafeteria or restaurant, whatever, right? So we are not just talking about the people here. How about cars? Cars waiting to be repaired in the mechanic shop, or airplanes waiting to take off or to be landed, right? And we have become accustomed to considerable amount of waiting, but still get annoyed by unusually long waits. Is that right? So queuing theory is the study of waiting, and it uses queuing models to represent the various types of queuing systems that arise in practice. Okay? And providing too much service capacity to operate any types of system involves, of course, excessive amount of cost, right? But not providing enough amount of service capacity also results in excessive waiting, right? And all these unfortunate consequences, I'd say. Is that correct? Okay, so here's some example of the implementation of the queuing models. Maybe in this example, we are considering the emergency room of any typical hospitals. Okay, so think about when you walk into the waiting room of the emergency room, you will need to check in at the front desk, of course, right? Sometimes you need to wait. And after checking in, you will be referred to a triage nurse, is that right? So who is trained to assess the severity of your conditions, and he or she will determine where and in what priority the emergency physicians will care for you. Is that right? So basically, the most seriously ill and injured patients are always seen first. Is that right? And then patients with less serious conditions will be seen after the critically ill patients are seen first in any emergency room. So if you are asked to wait in the waiting area, that means more critically ill patients are being treated ahead of you. Is that right? So basically, you are going to wait maybe 30 minutes, about an hour, 2 hours, maybe longer than 2 hours. From my past experience, I've been to the emergency room more than a couple of times, because a couple of times related to my wife's delivering babies or some other personal emergency situation. But most of the time, I've waited like more than 2 hours for sure. Okay, so actually, you never know how long you're going to wait until you see doctor over there. So there may be lots of complaints, right? At a certain point in time. So the hospital manager may consider to add another doctor and a triage nurse. The queuing models will be used for making such decisions. Okay? And to describe a queuing system, an input process and an output process must be specified. So some examples of input and output processes are given in this screen. So the input process is usually called the arrival process. So the arrivals are called customers. And in all the models that we discuss in this course, we assume that no more than one arrival can occur in a given instance. So for a case like a probably restaurant, this is a very unrealistic assumptions. For example, if more than one arrival of a group of people, for example, if whole family members arrive at the restaurant, then this is not the case, right? So in that case, we may think the bulk, which is the batch arrival, bulk arrival or batch arrival. Okay, so in that case, we can allow the bulk arrivals. Or models in which arrivals are drawn from a limited number of populations are called finite source models. Okay, I believe a while ago in one of the example problems that we discussed, we considered a job shop, okay, that consists of only, 2 or 3 machines and maybe small number of repairmen, right? So in that kind of example, the total number of population is limited to 2 or 3 machines, okay? And if a customer arrives but fails to enter the system, we say that the customer has bugged, okay? Another example we considered earlier, what is that, the local takeout restaurant example. Do you remember that? Okay. That local restaurant has a very limited number of waiting spaces. So during the frigid winter weather, when customers arrive and he or she find the restaurant is full, then he will gonna instead go to the next door, which is the pizza restaurant. Do you remember that? Right? So that is the case of bugged. Okay, bugged arrival. Okay. And the next, to describe the output processes, which is often called the service process of a queuing system, we usually specify a probability distribution. That is the service time distribution. Okay. Of course, that governs a customer's service time. And in most cases, we assume that the service time distribution is independent of the number of customers present. That means, for example, that the server does not work faster when more customers are present. Okay? We're assuming that the service time distributions is independent of the total number of customers in the system. And usually exponential distribution is assumed in practice. And we study 2 arrangements of servers. First is servers in parallel system and servers in series system. Okay? So, like it says, servers are in parallel if all servers provide the same type of service. The customer needs only pass through one server to complete the service. Whereas the servers are in series if a customer must pass through several servers before completing the service. So usually we are assuming that the servers are in parallel, okay, unless specified otherwise. Okay, now the sample examples of input and output processes are given in this table. Okay. Okay. Next, let's talk about the queuing discipline or service discipline. Okay. So the queue discipline or service disciplines describes the method used to determine the order in which the customers are served. Okay? And the most common queue discipline is, of course, the first come, first service, okay, discipline. In that case, customers are served in the order of their arrival. Okay? And in certain situations, we can consider LCFS, which means last come, first service. Okay? And also we can consider SIRO discipline, that means service in random orders. Okay? So if the next customer to enter the service is randomly chosen from the all the customers waiting for the services. Okay? Okay, so this screen shows some basic queuing process. So customers who require service are generated over time by an input source. Okay? So input source as the people in the case. Okay? Yeah. Okay. And then customer who require service are generated over time by these input sources. And customers enter a queuing system and join the queue. Okay? This is the entire queuing system. And if the server is not available, then they have to wait in the queuing line, right? And queue discipline rule is used to select a member of the queues for service. And the service is performed by the service mechanism here. Okay? And the customers leave the queuing system after they've been served. Okay? So this is just basic queuing process. Okay? Okay. And next, let's talk about the Kendall's notation. Earlier, I talked about this just briefly, right? When you talk about the burst process. So many of queuing models assume that all the inter-arrival times are independent and identically distributed. And that all the service times are independent and identically distributed as well. And such models conventionally labeled using what is called Kendall's notation. Okay? And this standard notation is used to describe queuing system in which every arrival waits in a single queuing line. Okay? So whoever comes in the queuing system, they have to wait in the single queuing line. Okay? Until one of the identical parallel servers becomes free. Okay? And then the first customer in the line enters the service, and so on. Okay? And in the Kendall's notation, Kendall devised this 6 different characteristics, okay? And each of these is described mathematically. And they determine tractability of efficient analytic solution. However, I should let you know that only a small set of possibilities are actually solvable using the standard queuing theory. Okay? Okay, so the first characteristic specifies the nature of the arrival process. Okay? Which means it shows the distribution of the inter-arrival times. Okay? Okay, so suppose jobs arrive at times T1, T2, and so on until Tj. Then let's define random variable. Let's say tau j. There is the T sub j minus T minus T sub j minus 1. Okay? So basically, tau sub j is the inter-arrival times. Okay? Then there are many possible assumptions for the distribution of these inter-arrival times. And typical assumptions for these inter-arrival times are independent and identically distributed, which is IID. Okay? And many other possible assumptions include bulk arrivals, okay, that we just talked about, or bugged. Okay, so customers will go away to other system. And for the Poisson arrival, the inter-arrival times are always independent and identically distributed, and inter-arrival times always follows exponential distribution. Do you remember that? Very early in this semester, I just briefly mentioned that if the arrival process follows the Poisson distribution, then inter-arrival times always follows the exponential distribution. Okay? That is mathematically proven. So if you want, you can find the corresponding material. And actually, other common arrival time distributions includes probably L-long distribution and deterministic distribution, or probably general distribution with a specified mean and variance times. Okay? Okay, the second characteristic specified the nature of the service times. So as with arrival processes, there are many possible assumptions. Most common assumptions are the IID, okay, random variables, and exponential service time distribution. Okay, the third characteristic is the number of parallel servers. And just to let you know, the servers may or may not be identical. Okay? How about the fourth one? Fourth character specifies the system capacity. That is the maximum allowable number of customers in the system. That includes the customers in service. Okay? And this number may be finite or infinite. And this number can be omitted if it is infinite. Okay? And the next, fifth characteristic gives the size of population from which customers are drawn. So this number shows the total number of potential customers. Okay? And it may be also infinite or finite. And this number can be omitted if is infinite. Okay? And the last characteristic, sixth characteristic, describes the queue or service discipline. So it determines allocation of customers to servers. And it affects the nature of the stochastic process that represents the behavior of the queuing system. And default value for this is first come, first service. Okay, that's the default. So if it is omitted, it is assumed first come, first service disciplines. Okay? Okay, so can you tell me what this Kendall's notation represents? It's exponentially distributed into arrival times and also deterministic service times, right, here, which means constant times for the service. And there are 10 servers in this system, and the system capacity, the maximum allowable number of customers in the entire system is 40. Okay? So in that case, how big is the waiting room size, for example? $30. Why is that? Because the entire system capacity is 40. That includes 10 customers being currently served. That's why I'd say the size of the waiting room is only 30. Okay, does that make sense? Okay. And here, the total population of 2 customers, which means this queuing system considers only 200 customers. Okay. And here, the service in random order service discipline is implemented in the end. Make sense? Okay, what about this? This is very fundamental queuing system, which is MM1, right? So this model assumes that both into-arrival times and service times have an exponential distribution that has the Markovian property, which is memoryless property. Okay? And the number of servers is restricted to be exactly 1. Is that right? Okay, now what if I change the second characteristic to, for example, G? So we have MG1 instead of MM1. What is that? So in that case, this model assumes that into-arrival times have the exponential distribution, but it places no restrictions on what the distribution of service times must be, because we assume that general distribution. Okay. And just to let you know, if the into-arrival times do not appear to be exponential, they are often modeled by an Erlang distribution. Okay. Okay, then how about this? Can you tell me? I'd say this might represent a small health clinic that has only 1 doctor, maybe, because number of server in this queuing system is 1. And the inter-arrival, exponential inter-arrival times, and 2-phase Erlang service times. Right? The total capacity of 20 patients in this system. Okay? So like most outpatient clinic, this health clinic can receive an infinite number of patients. That's why the fifth character was omitted, but you can put it here. And the sixth characteristic, first come, first service, discipline is also omitted. Okay? So this is exactly the same as this. Okay, now let's talk about Little's law. We already talked about this once, right? So this is very important result. And the formal proof is due to Dr. Little back in 1960s, early 1960s. I can remember exact year, but it's either 1960, 61, 62, something like that. And this law applies to any queuing system having a steady state distribution. And it relates mean queue length to arrival rate and mean response time. Okay? Of course, R stands for the average number of customers in the queuing system. Lambda bar is the average arrival rate of the customers. And W is the average time spent in the entire system. Okay? That including the time in the queuing line plus the time in the service. Okay? So that is the time spent in the entire queuing system. And with these small modifications here, we can also say two different things, actually three different things, which is RQ equals lambda bar WQ. Here, RQ is the average number of customers waiting in the queuing line, okay? And then WQ is the average time the customer spend in the waiting line, in the queuing line, okay? And also we can say, let's say, maybe LS equals lambda bar times WS. What is this LS? LS is the average number of customers in the service, okay? Likewise, WS is the average waiting time, average time that the customer spend in the service. Okay? So if you add up this, WQ plus WS, you're going to get W. Is that right? Of course, if you add up LQ and LS, you're going to have R. Is that right? Okay, here's some real-world examples of the queuing system. So commercial service systems. So for example, customers waiting in a barber shop. Okay, that can be a good example for that. How about transportation service system? You may think of cars waiting in the toll booth. Okay, how about social service system? What about people waiting in a court to see a judge? Okay, so you can just name it. There are a lot of good real-world examples out there. So if you consider a typical bank, let's say there are only 5 tellers in that bank, that typical bank. So customers form a single line, okay? Whenever you are getting into the banking, any bank, there is only one single line, right? Unlike the McDonald's McDonald's. So if you go to the McDonald's, there are different number of lines. Okay, depends upon how many cashiers, right? But let's talk about bank. Every bank has only one waiting line, is that right? So customers from a single line in a typical bank, and they are served based on the first come, first service, right? Discipline. Excluding a run on the bank, the waiting room is effectively infinite. And if you think of a very large size bank, the population of the customer can be effectively infinite. Is that right? And of course, the bulk arrivals are possible if several friends arrive together for service. What about service time and the inter-arrival time distribution in that case? Actually, you can go and measure it, right, with a watch at the bank. Maybe that works. Or you can make mathematically simplifying assumptions. Okay, so either is fine. And for the latter case, the most common would be the exponential distribution. Okay. Okay. Then let's take an example, very simple example. Let's suppose that Tertiary Cinema 12 in Las Cruces has 2 ticket sellers who answer phone calls and taking incoming ticket reservation using a single phone number. Okay. And so last Friday I've been to the movie theater here, Tertiary Cinema 12, so this is true. And in addition, 2 callers can be put on hold until one of the 2 ticket sellers is available to take the call. If all 4 phone lines are busy, a caller will get a busy signal and waits until later before trying again. And calls arrive at an average rate of 2 per minute. So we suppose the time between the arrival of the phone calls at the cinema is exponentially distributed with mean of 30 minutes. Is that right? It's a mean of 30 seconds, actually. Is that right? Okay. So the memory rate property of the exponential distribution implies that no matter how long it has been waited since the last call arrived, the ticket seller would still expect to wait an average of 30 seconds until the next call arrived. Is that right? The ticket reservation service time averages 20 seconds and is also exponentially distributed. Now we want to determine the following 3 things. What is the fraction of the time that each ticket seller is idle? And the fraction of customers who get a busy signal? And the average waiting time on hold. Okay, so to answer these questions, we need to build up the queuing model, right? So basically we need to draw the transition diagram. So let's do that. Okay, first we need to define the state of system. So how do we define the state of system? How about number of callers? Okay, so let's define the state of system. Number of callers. Okay. Then 1, 2, okay, see. So there are 2 ticket sellers, right? They are answering the phone call. And in addition, 2 callers can be on hold. And the next line saying that if all 4 phone lines are busy, a caller will get a busy signal. Okay. So, what is the system capacity in this cinema? 4. Is that right? 2 callers can serve the customer. In addition to that, 2 callers can be wait. Is that right? So the maximum capacity of this system, queuing system, would be 4. Up here, we are going to put the arrival rate of the course, which is given as 2 per minute. Is that right? So we're going to put 2 per minute. This is 2 per minute each, right? Once there are 4 calls already, then whoever calls next will get a busy signal. Is that right? Now, what about the service rate? If there is only 1 call, then what will be the service rate? The service time is 20 seconds. 20 seconds. Mean service time is 20 seconds, which means 3 per minute would be the mean service rate, right? So here we have 3 per minute, right? What if there are 2 phone calls? Would that be still the same? It's going to be 2 times 3 per minute, is that right? Because there are 2 callers. They can take care of both customers at a time. So you need to multiply by 2. If there are 3 callers, then since there are only 2 servers, the service rate is still the same, 2 times 3. Likewise, even if there are 4 calls, service rate is still the same, 2 times 3 per minute. Of course, in this case, if there are 3 calls, then 1 caller is on hold, right? In state number 4, then 2 callers are on hold. Is that right? And, this is Another good example of birth-death process, right? The number of population increased by 1 and decreased by 1. And customers' arrival and service are independent of each other. So we can use the streamlined version of the balance equation, which is 1 over pi 0 equals 1 plus first arrival rate over first service rate, the product of first 2 arrival rate, which is 2 square over 3 times 2, 3, which is 6, and then product of first 3 arrival rate, product of first 3 service rate, 3 times 6 square, right? And then product of the first 4 arrival rate over product of the first 4 service rate. Sorry, this is going to be 2, right? Two. So from here, you should be able to get pi 0. Is that right? Of course, pi 1 would be 2/3 times pi 0. Pi 2 would be this times pi 0. Pi 3 is this times pi 0. Pi 4 is this times pi 0. Okay? Oh, by the way, I forgot to tell you. So, using the Kendall's notation, how do you express this queuing system? We're assuming that both into-arrival times and service times follows the exponential, right? Which is Markovian property. So it's MM. And the total number of server, in this case, is 2, right? How about the maximum capacity of this system? That is 4, right? And we are considering the infinite number of customers. Is that right? And we are also considering first come, first service. So FC, FS. And you remember the last 4 characters can be omitted if it is infinite number or first come, first service. So actually I can omit this. So this is a good example of MM24 system. Make sense? Okay? Okay, so how do you answer for the first question? It asks you the fraction of the time that each ticket seller is idle. So if there is no customer, there is no callers, then each ticket seller is idle, of course, right? So it's going to be pi 0 plus what? What about this? If there is one caller, then only one of them, one of the 2 servers, is idle. Is that right? So only 50%, 0.5 of the server will be idle. So this is it, right? What if I ask you the fraction of the time that both servers are idle? Then how do you answer? Of course, it's just pi 0, right? Okay, how about second question? The fraction of customers who get a busy signal. Pi 4, right? If there are 4 callers, then the next caller will get a busy signal, right? So I'd say it's just pi 4. So from this, you should get all of these values, numerical values, right? Then how do you answer for the third question? The average waiting time on a hold. So average waiting time on hold. So I'm asking you W? No, I'm asking you WQ, right? If I just ask you, what is the average waiting time? Then it's W. But because I ask you the waiting time on hold, that means waiting time in the queuing line, in the waiting line. So you have to include subscript Q, which means you're going to get LQ first. So that later on, using the leader's formula, which is this, you get WQ. Okay? So let's get LQ first. How'd you get this? What is LQ? 2 times that is the number of customers on the queuing line. Is that right? So in that case, how much is that? For all of this state, that's going to be 0, right? If there are 0 caller, then there is nobody on hold. If there is 1 caller, still nobody is on hold. If there are 2 callers, still nobody is on hold. Is that right? So that's going to be 0 times pi 0, 1 times pi 0, pi 1. I'm sorry, 0 times pi 0. 0 times pi 1 and 0 times pi 2, right? If there are 3 callers, then 1 caller is on hold. Is that right? So 1 times pi 3. Likewise, if there are 4 callers, then two of them are on hold. So 2 times pi 4. If you do this, you should be able to get LQ. Okay? Then how do you get lambda bar? What is the lambda bar? That is the average arrival rate. So all of this state, the arrival rate is 2, right? Except for state number 4, which is 0 arrival rate. So you need to count on that. That's going to be 2 times pi 0, pi 1, 2, 3, and 0. Like that. Is that right? So once you get lambda bar, then you should be able to get WQ. Does that make sense? Okay, easy? Okay, so this is all for today, actually. So next time, I will give you another lecture about the queuing system, little bit more in detail, and also I will going to brought you some exercise problems. Okay, but just to let you know, if you are interested in the queuing theories, then we offer queuing system course is by Dr. Molin's class. Is that IE 522? Is that right? Maybe. I'm not quite sure, but I recommend you to take that class. So from that, you're going to get more in-depth theories and analysis about the queuing system. Okay. So in this class, I just give you some briefly overview and give you some idea what the queuing system and how it can be implemented to the real-world system. Okay? Okay, thank you very much. See you later. Thank you. See you later. Thank you. Thank you, Raman.